minus. Okay, it's going to be negative. The rest, we don't know yet. Okay, the rest, not don't know. But if we look at this formula, we don't have any moment in the y direction. So this is equal to 0. We don't have moment in the y direction, right? However, we have moment in the z direction. And we look at moment in the z direction. So the moment in the z direction is acting this way. Okay, the moment in the z direction is acting that way, right? And I'm going to draw a green dot. Okay, I'm going to draw a green dot. This green dot over here, right, represents the neutral axis. Okay, the green dot represents the neutral axis. So something new that I will teach, I will teach you guys. If moment in z is that in that direction, the head of the moment arrow is always going to be compression. The tail end is going to be what? Tensile. Okay. The head will be compression of the moment vector. The tail end will be tensile. Okay. So now once then we over here we form a table. Now anyone have any questions so far? Anyone?
Hey Eugene, could you explain the part about the tensile and compression part?
Okay. So over here, right?
Yeah.
This diagram over here, am I right?
Mm-hmm.
So if you look at the moment vector, okay, so this is the moment vector that I've just drawn, right? The head end of the moment vector will be compression. The tail end will always be tensile. That's it. Okay. Now later, either later in this class or on Friday, I will show more examples on this. Okay. Is that okay?
I'm sorry, I'm just having a hard time visualizing it.
So
I feel like I'm.
you can see this is the head end of the head of the arrow. Am I right? Of the vector, yes?
Yeah.
It's always compression. The tail end, I'm highlighting over here, is always in tensile.
Oh, okay, okay.
That's it. Okay?
Oh,
As I
okay.
said, I will elaborate more later on. Okay?
Okay, thank you.
So now, if we look at the elements, okay? If we look at the elements. So elements. Okay? So element, we have A, B, C, and D. Okay? So if we form a table down here, and then we write axial loading. Okay, so we have axial loading. Now, all of them on axial loading, right? Axial loading means based on this formula over here. This is axial loading. Right? So we realize on axial loading, elements A, B, C, and D, all of them see the same thing. Okay, all of them are equal to minus px over A. 1, all of them is minus px over A. 2 minus px over A. 3 minus px over A. Okay. Now, then the next one we look at is your bending moment. Okay, you look at your bending moment. So we know our bending moment is mz over izz multiplied by y. Okay. So now if we are going to draw the same shaft again. Okay. So this is the same shaft. So I'm going to be organized over here. I'm going to write down the normal stress distribution. due to moment in the z-axis. Okay, so I'm going to sketch the graph now. I'm going to sketch a graph now, and you guys will probably seen this before. So this is your stress in your x direction, and this will be your y. Okay, this will be your y. Okay, so this is will be your y. Okay, so in moment in z, if you look at your moment vector, you have tensile at the top, compression at the bottom. So over here, you draw over here, right? Tensile at the top, compression at the bottom. Okay, okay, this is just I try to centralize this. Okay, my apology. I'm just too excited. Most of the time, my wife said that I need to take drugs to calm myself down. Okay, too much information. Okay, so this is the normal stress distribution. Okay, so at the top will be in tensile, the material pushing upwards. Okay, so this is the normal stress distribution. At the bottom, you'll be going into compression. Don't worry about sketching yet. Later on in this class, I will teach you more. Okay. So anything on the right-hand side on the center is 0. Anything on the right-hand side is stress X is tensile. Anything on the left-hand side stress X is equal to compression. And anything on the neutral axis is equal to 0. Okay. So now let me put in our element again. Element A, element B, element C, element D. So this is our element A, element B, element C, and element D. Okay, I hope I label them the same, A, B, C, D. Spot on. So you can see over here, element B and element D, you have 0 normal stress due to bending. Right? Because it's on its neutral axis. Okay, you can see the element A is in tensile or tension, element C is in compression. Okay, so you have to go into detail on the distribution. Okay, so now from here, you go back to your table, right? So going back to your table, we realize that moment in element due to bending moment, element B is equal to 0, element D is equal to 0, and this is because it is what? This is because it's on its neutral axis. Okay, so now when we go from here, we know elements is in tensile. So plus by mz over izz multiplied by y. And now this is equal to minus mz over izz multiplied by y. Okay. Now I'm going to ask you guys a question, and it's not too early. Based on what you see over here, which element will fail? Anyone?
Either A or C.
There's no either. Which one? Pick one. C. Okay. Right? Yeah. Okay. Pick C. Okay. Now, the students say A or C. You're not necessarily wrong. It's possible to be A also, if it is a brittle material. Brittle material usually cannot stand tensile loading. For example, concrete. Okay, but we are analyzing this structure not based on any materials yet. Okay, we are looking at its magnitude yet. And some of you say C, you are right. Okay, some of you say C. So number one, the highest stress will occur at number 1 for element C, then followed by element A, then followed by element B and D. Yes, those sort of ranking. So if you look at the ranking over here, what we have done, this will have the highest what? Okay, over here, this will have the highest compression. Okay, then on top, it will have the highest tensile. Okay, highest tensile loading. Assuming that mz over izz multiplied by y is larger than px over a. Liam, you're absolutely right. Does the ranking B or D really matters? Sasi, as I said, if it's a brittle material like concrete, where it cannot withstand tensile tensile loading, yeah, that is going to be a critical part. Okay, but now we are just analyzing the structure without knowing what material we are going to use so far. Okay, so now we are doing failure analysis. Okay, by looking at the formula and by understanding the distribution. So next, okay, next, we are going to look at the torque. Okay, we're going to look at the torque in the x direction. Okay, so if we look at the torque now, okay, so let's look at the formula for torque. So torque is equal to or torque will generate shearing stress and you guys have seen this formula before, where torque or shear stress, okay, tau is equal to TR over J. Okay, it's dependent on the radius. Okay, right? It's dependent on the radius. And I'm going to draw. Okay, so if you see the torque, okay, so the torque in the is going about this way. In the x direction. Okay, so how the material will deform, okay, I'm going to draw the shear stress distribution. How the material will deform in this direction. So this is the shear direction. Okay, so some of you might ask me, Eugene, the shear is in, so that is the arrow. What direction is that? Okay, so I will tell you this first. Okay, so it is shear. Okay, let's not worry about the direction first. Okay, I don't want to confuse. Later on, then I teach you. Okay, so this is inducing the shear, which is equal to TR over J, and all of them are related to the radius. So if I draw the elements first, okay, so this is your element A, element B, element C, and element D. They all they all will have the same shear ring stress due to the torque. Okay, so now we know based on shear, right? Based on shear, all of them will be having shear, will be having TR over J, right? And it's going in this direction. TR over J, TR over J, TR over J. So in terms of shear due to the torque, it's very it's all constant. Okay. The next question that I think a lot of time, even trained engineers have a lot of issue. Okay. Now, Young asks, do most material withstand compression better than tensile? Young, Yes. Okay. However, in brittle material, right, like concrete, they are no good in tensile, or ceramic. Okay, they are no good in ceramic. Now J over here, okay, J over here is the polar second moment of area. Okay. Right. Now, the next thing that I want to highlight is this. A lot of trained engineers could not differentiate the difference between torque. When is it a torque and when is it a moment? And I want y'all to get this straight early, like now. Okay. I mean, when I say early, not in terms of good morning, early as being a young engineer. Okay. Because I met a lot of engineers, they